please take it from here.
Yeah, thanks a lot. The talk is named How We Keep the Power On, Elixir at the Core of a Virtual Power Plant. Yeah, my name is Johannes Weißl-Muhs, pronounced correctly, and I lead a team of software developers at Sonnen, and my colleague Jens Fischer, Elixir developer and Erlang enthusiast, sadly cannot join in person today because he's sick, but thanks for organizing this amazing hybrid setup, and thanks for doing this with us. We will tell you what our company does today, how we use Elixir for it, and what we have learned along the way. Next slide. So the main product of Sonnen are residential and commercial energy storage systems, which we will just call short batteries in this talk. And for all of the non-German speakers, Sonnen means sun, so the multiple for sun, because the batteries store energy from the sun. That's the catch. It was founded 15 years ago in Allgäu, and since 8 years there is a VPP team in Berlin. This is also the time when Jens and me joined the company. And since 2019 we are 100% daughter of Shell. Next slide. Yeah, so here you can see what such a battery actually looks like. It is the black box where the red arrow points to. They are often also in the basement, but here for this marketing picture, they are here. And homeowners usually buy such batteries to, like I said, to store excess solar power from their PV panels into the batteries to use them later in the evening when the sun is not shining for household consumption. But there are other use cases for the batteries, and this is where our team comes into play. Next slide. So what is a virtual power plant? A virtual power plant is not virtual like programming code. It's not, you can touch it. The virtual aspect is that the power resources are distributed across long distances. So yeah, this is the virtual power plant. It's distributed, but still acts like one power plant that is in one place. And such virtual power plants are not used for continuous power generation, like a nuclear power plant or a coal power plant, but on demand. For example, to participate in trading markets, energy trading markets, or to stabilize the local or non-local power grid. Next slide. The VPP at Sonnen aggregates tens of thousands of these small residential batteries and also some EV car chargers. This is really a specialty. Normally, virtual power plants are made out of bigger assets, but these are tiny, small assets, but 10,000 of them. And they are in many countries, but we have the VPPs. For example, we have one VPP in US and one in Canada and one in Germany. They are not connected in any way. So in US, they are hosted in AWS Oregon, and they are not connected. Yeah, and they support also different products in different countries. But for this talk, we will just focus on frequency containment reserve in Germany. So yeah, but just know that there are different products overall in the world. Okay, next slide. Yeah, frequency containment reserve in Germany is one method of the so-called TSOs, the transmission system operators, to stabilize the power grid. You may not know, but the energy that is produced must match exactly the energy consumed in the power grid. If this is the case, then we are at 50 Hertz grid frequency, and then it's all good. But if we deviate too much, then we risk going into a blackout. So the TSOs, you can see Germany is divided in 4 zones, which you might not know, but not in 2. And they they are responsible to stabilize the power grid and use something like FCR. This is the fastest product. There are slower ones as well. They use it for it. It's an open market. You can participate if you pass a so-called PQ test, pre-qualification. It is a very rigid, strict test, and if you pass it, you can participate. And if you mess up, you lose it. Then it's very bad. And you can participate in this auction only in 1 megawatt blocks. So normal household batteries could never participate on their own. This is what you need the virtual power plant for. So you can only participate if you aggregate many. Yeah. Next slide. Okay, this is an actual screenshot of our system in Phoenix Live View. I don't have a mouse here, so I ask Jens to be my mouse. We can see in the middle of the graph, if we can see a gray line that is above the big middle line. Yeah, here. This means this is the actual grid frequency last week, late at night when I made these slides. Here we can see the grid frequency is above 50 Hertz. This means we have too much energy in the grid. So our batteries, they charge from the grid. The batteries get fuller. We take energy off the grid to stabilize it. Yeah, the orange line is what we should do, and the green line is what we did. All good, close together. And then at 10 p.m. in the evening, we can see that the grid frequency drops sharply. This is not unusual because at the full hour, normally regular power plants go into the grid or out of the grid, so this is not unusual. And now the batteries discharge into the grid to give it more energy to stabilize it. So yeah, and it happens of course automatically. But yeah, next slide. So how does it work exactly? The batteries measure the grid frequency locally. So every battery measures the grid frequency locally and also reacts locally. It would be too slow to go back to the server. But the catch is our brain, the batteries don't react at the same frequencies. So we calculate at which frequency a battery should react. And this is because the battery owners, of course, want to use still their batteries for the original use case. They don't want to stabilize the grid all the time. So not all batteries participate, and not all at the same frequency deviation. And also some batteries are right at this time they are better fitted to stabilize the grid, so they get lower bounds. So this is where all the intelligence of the system is. And it's calculated every 10 seconds, the optimization is run and new bounds are distributed. Next slide. Yeah, one other topic I want to talk about are the very strict IT requirements. The TSOs it's their market. They are responsible to stabilize the grid, so they can make incredible rules. So this is a screenshot from their guidelines, which we sometimes call our Bible, because we have to strictly adhere to it. One thing is the system needs to be like twice. You need to have 2 data centers with the same system as redundancy. They need to be far apart. This is one thing. And also the green circle you see here, where all the logic is happening, it cannot be connected to the internet. So the red is the dangerous internet part here, green is the non-internet free part. And you might wonder, how do we get data then from the batteries? Surely over the internet. But every data point we receive from the batteries needs to traverse through serial cables. So TCP is not allowed. The older ones might remember serial cables. This is in German it's called Medienbruch. Yeah, so it's really a lot of rules, and this is also why we don't have it in AWS like for other countries, but we have it in our data center with our own hardware. And with that, I hand over to Jens for the even more technical part.
Yeah, hello from me as well. So sorry to not be there in person, but I guess I'm kind of a health Yeah, so thank you to Codebeam for making it possible to do it like this. Let's talk about the tech now. Here you see the main components of our distributed service architecture. On the left, you see of batteries, like our thousands, tens of thousands of batteries, the household batteries, residential batteries Johannes talked about. Our custom client software. This is a piece of software that is written in Rust. And the purpose is to steer the batteries and the backend. Then you have the backend itself. This is the main entry point for the batteries. They provide a gateway for the batteries to connect. And the backend is responsible for distributing the data streams I will talk about in other slides within the system. For the backend, there are multiple instances of each service running in parallel for scaling and redundancy purposes. Then, this is the brain Johannes mentioned. In our system, it's called the controller. The main function of the controller every few seconds. And the controller is written with a mix of Elixir and Rust, like the computational parts are written in Rust, where we do need to do a lot of number crunching, and the orchestration around is written in Elixir, as is client is mentioned in Rust. We have parts of the controller in Rust, but the whole rest of the system, backend and front ends, all the different services we're not mentioning. All of this, and this makes up the majority of the system. All of this is written in Elixir. Then we have the front end, or what we call it is the interface to the transmission system operator, the grid operator, or to other market partners in other countries. Part of the front end is also a web interface and APIs to monitor and control our virtual power plant. Then in we have used two databases. These are our two main databases, two distributed database, Cassandra, where we store time series data, DB for storing operational data. Now let's look at some more. One way of explaining our system is to describe the main data streams going into our system. The biggest one by volume is what we call readouts. What is a readout? A readout, so one single readout, measurements, currently around 60 different data points coming from the battery. So these are things like power meter readings, power meter readings from the grid connection point, the frequency of the power grid, capacity of the battery, the current state of charge, things like these. And we send these in the German system every 2 seconds. We vary that a little bit between systems. We are able to do it. In the German system, we do it every 2 seconds. In other systems, we do it a little bit slower. For some batteries, we do it a little bit faster. But if you have tens of thousands and send data every 2 seconds, you can see that that becomes quite a bit of data quickly. Then we have the client that is creating these reads outs actually from different data streams. So from the different measurement devices, there are different data streams, and these are bundled into a readout and then sent to the backend. The backend is responsible for persisting this stream of raw readouts to Cassandra, and also forwards the readouts to the controller. It does with regard to data processing, it does two things. First, it calculates for every receive, so for every readout per battery, it calculates derived data points, so some could say an enrichment of the data. And then the second thing it does is it aggregates many batteries into clusters. So to the external viewer, and from the controller onward, it only deals in what we call clusters. You could say this is like a big virtual hundreds or even thousands of batteries get aggregated into a cluster, into one virtual battery. These clusters are then forwarded to the front end. There they are processed a little bit again, depending on the requirements of the market partner, and are forwarded in the German system to the grid operator as telemetry for monitoring. And both kinds of these data streams are, so the derived, the aggregated signals are also persisted in Cassandra. Now we know how our system receives data from the battery, but it wants to control the batteries, of course. So how does this work? This is the task of the controller. The controller, just as described, calculates the signals. These both are optimization that is run every few seconds, every 10 seconds. The controller is running an optimization, and the output of this optimization are these commands are generated, one command for each battery. And for our example, what Johannes explained, we generate these individual frequency bounds per battery. So we have this frequency. These are then sent from the controller back to the backend, and it's the task of the backend to send these commands route the correct batteries. The batteries then install the frequency bounds. So once the locally measured frequency has one of the frequency bounds of this individual battery, then the battery starts to charge from, or to starts to discharge into the stabilize it. And together, all the hundreds and thousands of batteries, all these tiny reactions make up the whole response that we saw in the graph from the web interface Johannes was showing earlier. These reactions are all reflected in the readouts, because the battery measures what it's doing itself. And these readouts are sent back to again, and in turn inform the next round of commands. So through the readouts and the commands, the controller together form what you could call a distributed feedback control loop. I have a rough overview of the system. I want to talk about another aspect of our system: redundancy. As explained, this is a requirement by especially the German regulator. Specifically, the requires that we have geo-distributed redundancy with at least 2 locations. They even prescribe a certain amount of kilometer, this amount of distance that needs to be between these 2 data centers. And this is the reason the system runs in 2 different locations, in 2 different data centers. Our system, we always have one active system and one standby system, and this means we need to select the active side. And selecting the active side in a distributed system, this is what's known as leader election in distributed system theory. To this, known solutions to this, and these are consensus algorithms. You probably heard of Paxos or Raft. And yeah, they solve this problem of distributed leader election. But for consensus, you need voting. For voting, so this means we actually need to have a third side. So we added a third side to our system. Still need a consensus algorithm, and as distributed systems, people like to say consensus is a bit cryptography. You shouldn't implement it yourself. So we didn't. What we did is we used cockroach and do the heavy lifting. CockroachDB is a consistency-focused distributed database. So in CP database, but I want to go into this here. But it's consistency-focused. It uses Raft as a consensus algorithm. It's well tested. And then we used on the basis of CockroachDB, we used this to implement a lease algorithm based on an academic paper. This paper itself uses what they call an atomic registrar, which is kind of the small consensus algorithm for a consistent space storage unit. And so we did to implement this atomic registrar ourselves. We used Cockroach for this, but used the algorithm from the paper. And at least I like to think that this is a solution to combine it this way, because we get well tested. We have a proven algorithm from the paper. We have a well tested implementation, but we can still tailor it pretty good to our needs. So how does it look in a little bit? We have a hot standby model. This means we always have one active site. Here in the picture, it's the blue side. And in normal operation, this is the hot in the hot standby. In normal operation, we use both of these locations badly or similarly. Data streams, the readout data stream is fed into both locations. All the components are always but some components behave differently depending on if they are in the leader side or not. So how do we? The batteries randomly choose an entry point, a gateway to connect to, and by this they randomly choose a site to connect. We should have roughly 50% of the batteries connecting to each side. We then have a connection between to fan out or mirror the readout traffic so that both systems receive not only half of the readout traffic but the full readout. This then goes to both of the backends. The backends are mostly unaware of the leader status. This means they behave the same whether they are in the leader side or not. The data gets written to Cassandra by the local, so both locations. So each location is only writing the readouts from it directly receives. This is one of the reasons why we needed a distributed database here, because the system needs to be able to write data into Cassandra and to read from Cassandra, even the network split. The controller is then one of the components that needs to be aware of the leader status, because only an active site is generating commands. So you cannot have two controllers that are generating potentially conflicts them to the battery. So here the leader election comes into play. The front end also needs to be aware of the leader status, because only the front end in the active side actually holds the connection to the grid operator and sends the signals there. So this is normal. Now let's look at what happens in case of network problems. We look at a scenario here where one side or the gets completely disconnected from the network. So it's completely isolated network-wise. This means node this side is talking to cannot reach the rest of the Cockroach installation anymore. So it's what we call in the minority partition. The leader election, the lease algorithm cannot renew the lease anymore. And once the lease expires, side 1 will lose its leader status. The other side, so side 2, still connected to the majority partition of Cockroach. So here the leader election still works. It can now acquire a lease because there is no active lease. Once the active lease is expired, the controller will then start working as active controller once it learns of the leadership. and the front end will re-establish a connection to the grid operator. The batteries were connected 50-50 to both sides. If side 1 is not reachable anymore, this does not work, of course. So they are migrated by reconnecting, and after a short while we'll choose the other side as the side to connect to. But one of the advantages of 50-50 connection to both sides is that in the case of a failover, we immediately have 50% of the locally connected. They don't change. They don't have to migrate. We can still continue immediately steering them. And it's good for overhead in the number of batteries. And if the frequency deviation is not too much, we don't need all the batteries. And with our around 30, 40, 56 seconds, we have a complete switchover and a healthy system again. This whole redundancy mechanism was, of course, also built in Elixir, and honestly, I wouldn't like to do it in any other language. I now but to explain a little bit in a little bit more detail why we choose Elixir and how the experience Elixir was for us.
Thank you. So these failover events, they usually happen only every 1 or 2 years. So it's very important that they work, because you don't, like, if it's happening, they need to work, but we don't often have such failures where you really need to switch the data center. Why Elixir? You heard a lot in the other talks about supervision trees, the inherent fault tolerance of Elixir. I mean, we have 2 data centers, but still, there are a lot of bugs happen or problems because of external input, and you have fast restarting processes. So Elixir is really, really good for this type of system where you basically we don't get any 99% number. It's more like if you commit to stabilizing the power grid, you need to do it, and if you fail too often, then it's basically over. So Elixir is perfectly well suited for that. Also for scalability. We are we're a small team who do this, and when we started 8 years, it was only a handful batteries, and now it's tens of thousands, and we did it with a small team and only without any major rewrite, just the same code base. So I attribute this also to Elixir. And I don't have code here, I should have, but in the other talks, they have done so nice network protocol matching. We had to implement a lot of energy protocols, and it's just beautiful how this works in Elixir. These are all reasons for Elixir. And then why Rust? When we started 8 years ago, we were told, don't bring another VM on the battery. We already have. So we were not allowed, sadly, to bring the Beam VM on the battery. Then we decided for Rust. And on the controller, it was for the signal processing is in Rust for speed reasons. But to put it into perspective, it's 200,000 lines of Elixir and 30,000 lines of Rust. So it's the system is an Elixir system with small parts in Rust. Next slide. Some closing remarks. We had in 8 years only 2 beam crashes. That's good. One was connected to a NIF in a crypto library that Phoenix used. So that was fixed bug. And one we had a few months ago, it happened and never appeared again. I reported it upstream, but I don't know. I talked to Erlang Solutions. I think it's probably a hardware failure. So very stable, very, very satisfied with the beam. Yeah, what we also learned is that maintaining distributed databases on our own, it's hard. So it's a lot of work. So Cassandra and CockroachDB, it's it is something. Yeah, and also if you want to build such a system, what we learned also the hardware is that you should think about back pressure or flow control early on, because doing it later is also hard. Yeah, and for everybody who thinks about writing a big system in Erlang or Elixir, it's and thinks about, oh, will I get programmers for this? Will I get good software engineers? I can say, yeah, we always found excellent people. It was in Berlin. It was not a problem to hire people. That's what I want to give away as a, yeah, for anybody who has this decision. Then next slide. We don't get the next slide. We get the next slide. It's also the last slide. So, yeah, thank you for listening. Yeah, we tested the audio setup, of course, before, but and it worked flawlessly. So, but I think you're all very intelligent and could make out the missing parts. Yeah, thanks to you and thanks to all the open source projects that are listed behind me that we use. Yeah.
So I know this is the last talk before lunch, but do we have some questions here? We have some minutes left. There's one over here.
Thanks for presenting this fascinating topic. I was wondering if you have tens of thousands of batteries, like do you always have to be able to reach all of them, or how many do you need to reach to be able to provide your functionality?
Yeah, it's a good question. We don't need every battery. Yeah, for us it's only the sum. So we have a headroom, of course. We have some criteria that we need to fulfill. For example, for 15 minutes straight, we need to deliver the full power that we committed to stabilize the grid. We always need to make sure to have this, for example. So that's what we need to make sure. About the exact numbers, we have people who know it 2 rows before you. You can approach them afterwards, but yeah, we don't need all.
And how much batteries do you need to have 1 megabyte chunk you can commit?
It depends on the size of the batteries. The batteries are 10 kilowatt or so, or sometimes larger. For 1 megawatt, I would say 1,000 or 350. Okay, the batteries got larger since I last had it in my head. 350 for 1 megawatt.
I also have a question. Did you notice the blackouts in Spain and Portugal in your monitoring?
Yeah, we could see them. Yeah, I think we also made a blog post, or not me, but the company made a blog post, so we could see them. But in Spain, we are not doing the frequency containment reserve, but in Germany, and it's all connected. The European power grid, it's all connected.
Maybe last one. Oh, there's one more.
Hi. In comparison to a power plant, how many power plants are 10,000 batteries? How can we compare the energy capable you're delivering?
So yeah, like 300 or 1 megawatt. I don't know. A nuclear power plant is, I think, a gigawatt or so. So it's 350 times 1,000. So 300,000, if I'm not mistaken, would be then one. When I made a mistake, it's hard to do math on the stage. But yeah, it's not this virtual power plant. It's not used like a nuclear power plant. It's not used to. Of course, the homeowners would be. We don't generate power here. We stabilize the power grid only. So it's not really comparison to a normal power generation power plant.
Yeah, there's one more.
about the frequency signal. Is this like something technical that you just, I don't know, happens that the frequency goes up and down depending on the utilization, or is it more like meant to signal what should happen, like it's to inform the providers of energy or the consumers what they should do?
No, it's an actual physical property. It's not like a signal for computer scientists to give as an incentive for the market. It's really, I think the talk before me can knows more about physics. So yeah, it's a measurable grid frequency, and it's yeah, if it must be, yeah, it's a physical thing.
How do you test your failover mechanism?
How do we test it?
Yeah, how do you make sure that it like... Okay.
Excellent question. Now we actually what we knew about the dangers of everything which is only in use for 1.5 years, so we use it also for upgrades. So that is what we use. Yeah, we do like we upgrade first the software on the one side, and then we simulate a failover to the one with the new software, and then we upgrade the other one. So that because it should, yeah, that is the big fear. Anything that is tested so seldomly, so we use it for upgrades. And every year or so, an admin of us goes into the data center and unplugs something. So because of course it's not a real test, but yeah. So yeah.